Dave Kaiser is a remarkable combination of physicist and historian of science at MIT and in STS, and he's taken on many other responsibilities at MIT, including integration of humanities into the new computing college. And he's worked on a great variety of topics. He wrote a wonderful book on the history of the Feynman diagram and the way it multiplies and ramifies into different interpretive schemes. And then he did a book, which I highly recommend as well, which is called How the Hippies Saved Physics. And it's about the early work on entanglement and entanglement-based technologies that came out of quantum mechanics, like just philosophical comments on the properties of the science, but now has morphed into a major area of technological work in a billion-dollar global industry, including the big Harvard Quantum Initiative here. He's done work connecting science, technology, and state in various ways. He's worked on the history of pedagogy. Anyway, that's a good start to Kaiserian studies. He's also a former student of mine, so we've been talking about things since I think he was a senior in college.
Yes,
so
it's deep.
goes back a long way.
I use Redshift now. Take his email so far in the bank.
Exactly. IZ friendship and colleagueship. Anyway, welcome, Dave.
Thank you so much. Very kind. Oh, thank you. It's always such a great treat to be back here at BHI, and I want to thank the organizers for your kind invitation. So I'm excited to share this work with you today. This is a part of a very, very slow, long-running and slow book project on aspects of the history of general relativity. And this will be really kind of the last main chapter of that, some fairly recent history in this case, as you'll see, 1970 to 1980s. And so I'm especially glad to hear comments and suggestions and feedback. This really is still working on this. So as you'll see, I'm going to be talking about the U.S. military.
That doesn't.
That's okay. I can point. I forgot. So aspects of Einstein's relativity, in particular general relativity, in a setting in which we might not first think about, not just beautiful settings like BHI or the beautiful EHT, but actually in things like, at the time, a highly classified military technology that we now know as a global positioning system. So, this. Okay, so GPS today, I hardly have to remind you, is just completely ubiquitous. I personally have a horrible sense of direction, so I rely on this literally to get out of my own kitchen in the morning. It's used in civil aviation. It's used everywhere. We all know in this room certainly what GPS is like. There's a really fantastic historical treatment by another one of Peter's and my colleagues, another one of Peter's former students, Bill Rankin, who's now teaching at Yale, called After the Map, which is really one of the cutting edge early histories of what grows into GPS. I've relied on Bill's work a lot for this. Some of the really nice books by some journalists and other historian of computing and so on. So I'm able to rely on now a growing literature on the early stages of GPS. What is GPS? Thanks to the Smithsonian, to the Air and Space Museum, we can put it down literally onto a single cartoon. This might be familiar to many of you. The GPS system these days relies on a network of about approximately 30 satellites in very specific medium Earth orbits. And the orbits are selected so that on many parts of the world, not every part, but in many parts of the surface of the Earth, there will be at least 4 of these satellites overhead within a kind of direct line of sight at any time. So our receivers on the ground, this is what they used to look like, now they look different. Our receivers are constantly receiving 4 different signals, one each from 4 different satellites. The signals essentially are saying, I'm here now. Here's my current location. Here's the time of my onboard clock. As you see, they have very fancy atomic frequency standard clocks on board. They're basically saying, I'm here now. And as you might imagine, if you get that from at least 4 different objects in motion relative to you, then you can start solving 4 simultaneous equations for 4 unknowns. You can use the fact that these are electromagnetic signals traveling at the speed of light to infer the distance from the receiver to the sender, compare the offset in your local clock time from what was reported, and then essentially triangulate or quadriangulate, which is to say infer your 3 coordinates in space and then your local time. And so by tracking information from 4 different things moving with respect to you, you get to say, oh, I'm here now. And that, again, at least in a cartoon version, is what we now many of us rely on pretty much every day. So once, especially in this room, once you start hearing about things like clocks moving really fast, sending light signals, some of us are going to think really quickly about relativity. In this room, all of us will, right? But even beyond this room, many people think about relativity. Clocks moving fast, trading light signals. So as we know, Einstein's theory of relativity predicts that both motion and even in the absence of space-time curvature, and of course, gravity will affect the measured rate at which a clock will tick. Here's a lovely popular book by colleagues you all know very well, Cliff Will and Nico Hunes. Is Einstein still right? And the answer seems to be still yes. It's a lovely popular book. And they write about a little bit about the incorporation of relativity into GPS, and I'll just let them explain to us. Without the proper application of relativity, GPS would fail in its navigational functions within about 2 minutes. That is, say, the errors, if not corrected, would propagate to the level of 7 miles, or roughly 11 kilometers per day. So next time your airplane approaches an airport in bad weather, and you just happen to be wondering what good is Einstein's theory, the first thing would go through my mind is turbulence. Think about the GPS tracker in the cockpit, helping the pilots guide you to safety. Indeed, the underlying physics of the ways to incorporate different kinds of relativistic effects into the operation of GPS is so well understood these days, it's been put into really lovely undergraduate textbooks on gravitation, like James Hartle's great book. So we have nice kind of sections, homework problems, even undergraduates can start wrestling with why we have to worry about different aspects of relativity to get GPS to work to the desired design accuracy. So we know all this now. We know it as a community, known it now for quite a while. And yet, as the usual historian's trick, we know that now. How did we get there? Long before this became a widespread, kind of ubiquitous consumer technology, it was, that is to say, GPS was a secret military technology. For about a decade within that span, a debate simmered behind the scenes among a whole bunch of experts, some theoretical physicists, whose names, again, you'll recognize in this room, some engineers, some military officials and planners, about how to incorporate relativity into GPS. And as a preview, the argument wasn't relativity, love it or hate it, it was who's getting the relativity correct. They already had come to a consensus that they needed to take these kinds of relativistic corrections into account, but then they still argued for many, many years, often quite heatedly, about who was doing it correctly. And not only worrying about things like a problem set or a press release from the EHT, they were worried about actually triggering nuclear war. Right? That's why the two pies really matter. Right? So these were bitter complaints about secrecy, about special interests, about expertise in the midst of very kind of high Cold War drama. So that's what I want to bring us back to. So I'll remind again, extremely briefly with this group, some of the kinds of relativistic effects that people identified that they had to worry about for things like GPS, and then turn the clock a little bit forward from there, in the earliest days of relativity, to say what are the origins of GPS itself, where that sort of parallel track come from, and then bring this together with these basically dueling relativists, much of the work being done at the time behind the scenes during the 1970s and the 1980s. That's where I'm heading today. Okay. So again, many of you in this room will know this very well. The history of Einstein's own path toward the general theory of relativity is one of the best documented episodes in the history of science. It's amazing. It's in historians and philosophers and sociologists' playground. Thanks to an international team, again, I'm sure many of you know many of the current members and past members, working on things like the collected papers of Albert Einstein. We have extraordinary documentation of this 10-year intellectual kind of journey that Einstein and a small circle of colleagues took in the early years of the 20th century. We also know, so we have, for example, his Zurich notebooks. I love these because he made tons of mistakes and crossed things out, gives me hope. He was bumbling, frankly, along on both some deep conceptual questions as well as some sometimes really quite elementary mathematics because he had cut a lot of classes as a university student. So we have amazing documentation. We have a growing body of synthetic secondary works trying to take some of these really very subtle twists and turns intellectually into account and bring them to the fore. But I'll jump to the conclusion, which everyone again in this room will know, that by the end of that journey, though certainly not the beginning, Einstein concluded that gravitation is, at least I'll say, deeply related to geometry. I know Dennis is on the call, so I'll watch my words carefully, Dennis. I'd like your clarifying work on this a big deal. Anyway, that gravitation is somehow deeply related to the warping of space and time. And so, as we all know, the field equations are deceptively simple to write down. They contain a lot of information about sort of the geometry of space and time, the rates of change, the warping and gradients here, to relating that to where the stuff is, the distribution of matter and energy. So we can now draw pictures like this, and thanks to the LIGO group, where we are very familiar with a kind of trampoline model of gravitation arising from the warping of the vicinity of large, dense, massive objects. The Earth is orbiting around the sun, not because of a Newtonian exchange of forces, but because the sun has warped or distended its own environment. There's a really terrific body of literature here again by many friends and colleagues who've helped us chart these early years, leading from the early 1900s into the first efforts to test these ideas in the 1910s and 20s. And I think I could recommend each of these books and many more. What's important and what often gets left out from these kind of trampoline-like figures or static images is, again, as well known in this room, Einstein's equation suggests it's not just space or spatial sections that are subject to this kind of warping or curvature, but also the local measurement of time. So I like to throw up Salvador Dali's melting clock as a reminder. There's a warping of the measurement of time as well as this kind of stretched trampoline of space. And that will be especially important for the GPS story today. Okay, so again, I'll go quickly for this part. There are several conceptually distinct ways in which ideas from relativity, both the special theory of relativity and the more mature general theory, should affect the measured rate at which clocks will tick. And the first goes all the way back to the famous paper on special relativity submitted to the journal in June of 1905 on the electrodynamics of moving bodies, where Einstein in that paper already introduces what we still call the light clock. So you all know in this room, we imagine measuring time with a pair of highly polished mirrors and bouncing a light beam between them. Einstein had convinced himself by this point that the speed of light was special. All, at least inertial observers at that point, should agree on its measured speed. So if you fix the height, then we should be able to use this as a standard clock if we hold it at rest next to us, and then watch as our friend races past us on a high-speed train, trains, and we'll watch her light beam carve out this sawtooth pattern where the time between ticks must be measured to be longer by us, because a light beam can't pick up speed to make up the difference, and it has to travel this hypotenuse of a right triangle instead of just directly straight up and down. So we, of course, call this time dilation. So even without having mentioned gravitation or warping space-time manifolds at all, we already have the first indication that how different people will measure a clock, an otherwise standardized clock to tick, will depend on things like the relative states of motion. Einstein then began thinking toward what would become the general theory of relativity as early as 1907, 1908. We have this documentation in great detail. And he returned to this idea as a kind of thought experiment a few times. His factors of 1/2 and 2 changed over the intervening 7 or 8 years. But he had this kind of picture in his head from early on. And that was what we would come to call gravitational redshift, again, for the person familiar in this group. So what if we have an emitter and observer both at rest with respect to each other, but a light beam being emitted from a region of strong space-time curvature, say a deep gravitational well, as we call it today. Then, of course, the light beam has to expend energy to climb out of that well, at least speaking as we would put it today. And if you relate that to its frequency will be shifted toward the red end of the spectrum. We can use these characteristics of the light beam as our clock. So we see the clock ticking more slowly if the light had come from a region of strong space-time curvature. We call that gravitational redshift. Easy to write down. Einstein got the mathematics, kind of jumbled it a few different times before he arrived at the expression we know and love today. And early on, several astronomers in many parts of the world tried to measure that, and it was completely ambiguous. This is actually very, very hard to measure in the early days, but Einstein at least had convinced himself of that by 1915. There's a third way, at least a third way, in which relativistic effects would affect the measured rate at which clocks will tick, and that has to do with rotations, and they're now known simply as the Sagnac effect. So let's imagine having identical clocks shifted around the equator of the Earth. And so we have observers with each clock, and they want to synchronize their clocks by trading light beams. So when this clock strikes 12 noon, that observer emits a light beam toward her neighbor, and so on to complete a loop. And so they can all say, so this recipient says, well, I should set my clock to be 12 noon, offset by the travel time. They know their relative distance, they know the speed of light. So that should be a way to synchronize all their clocks based on the first signal from there. What does that whole assembly look like to an observer who's not rotating, who's standing still, let's say at the North or the South Pole, who's watching all this whole other assembly observers rotate around? That non-rotating observer will measure this whole closed loop to take a different amount of time, because it's sort of a not fair baton pass, right? So once this clock has emitted its first light signal, the whole assembly has begun to rotate. the light beam has further to travel to complete the loop, at least as seen by the non-rotating observer at one of the poles, and there's a calculable offset, right? So it'll depend on basically the cross-sectional area of that closed loop. Sagnac first wrote this down really early after Einstein's first paper in 1905. Sagnac, of course, thought this was a way to disprove relativity, and it was clarified some years later by another French researcher, Paul Langevin, in the early 20s. This was actually a prediction, it's a feature of relativity, not a bug, right? This actually is predicted by relativity, and to this day we know it very well as the Sagnac effect. That's distinct from motion in among inertial observers, distinct from motion near a large mass. These are different ways in which relativistic effects should affect the rate at which clocks are measured to tick. Okay, so just to summarize these three conceptually distinct things, not all clear to all the whole community right away. This really was a lot of analytic and conceptual work among a growing community of relativists mostly throughout Europe at the time, with some observers, for example, in California and Australia trying to weigh in, but with ambiguous results. It was a model. And of course, the effects were extremely tiny, at least on everyday human scales. So these were much easier to write down on paper than to say anything definite about here. Okay, let me pause and now jump to the second part, GPS. This is what was one of the earliest GPS receivers. It was called, with no particular sense of irony, a man-pack. Yeah.
David, sorry.
Yeah.
The Sagnac effect is just kinematics, right? Motion. It's not frame drag.
No, correct. It's not lens touring, correct. I agree with that.
Is there another effect from that?
Sure, and of course, as you know, even more subtle in terms of quantitative.
Right.
Yeah.
For GPS, is it important?
My understanding is that is not incorporated, although there's others. No, that's a great, thank you, Raj. No, you're right. This, I remember, and it has to be kinematic because it was discovered during special.
Exactly, yeah,
So,
right, sure.
Good. No, that's a great point. So, wouldn't it be amazing if my GPS had to worry about lens touring effects?
Yes.
That's a challenge for the
Just
next
to spin on
generation.
the earth, yeah.
To my knowledge, that is not at all incorporated.
Well, at some point we'll live on black holes or live on
Yeah.
on stars.
I
That
think
will be
some of
important.
my colleagues might already. It's a longer story, Jeff. Even if email return rates. Yeah, so we have new challenges to. Anyway, this is now, let's talk about the military origins of GPS. As I said, you can see that a US Army, a person posing clearly a staged photograph. This is what we'd have to carry around if technology hadn't evolved since the late 70s. Man-pack. Okay, where does GPS come from? It comes from kind of quintessential early space age Cold War technology. So in early October of 1957, October 4th, I think it was, the Soviet Union launched the Sputnik 1 satellite. And many people all over the world got very interested in this, often very enthusiastic and excited, some very fearful. Some folks who were very curious about that included William Geyer and George Weifenbach, who were both research scientists at the Johns Hopkins Applied Physics Lab. Again, many of you will know the Applied Physics Lab was set up during the Second World War, just like many other contracting sites around North America and beyond, to work on, at the time, classified military defense technologies like radar, sometimes offense technologies like proximity, radar, targeting, and so on. The lab, much like almost all these labs in the US after the war, never demobilized. It remained a tightly coupled military contractor site associated with Hopkins, not right on the Hopkins campus, and doing a lot of high priority work during this new kind of Cold War era. And so Geyer and Weifenbach were also mesmerized by the Soviet launch. They realized a lot of their day-to-day jobs, developing techniques to do things like track guided missiles, they could actually start tracking Sputnik with the tools they already were experts on. Well, roughly 6 months after that, they realized they could actually, in principle, reverse the technique. What if they launched their own purpose-built satellite with a transmitter? They were beaming down, basically, I'm here now kinds of instructions. Could they use that to navigate their own location on the ground? You can already begin to hear this. It starts to sound very familiar to us in our GPS world. They proposed this to their supervisor, Frank McClure, as again, another stage photograph from the spring of 1958 at the physics lab. And as a reminder, this really was a Cold War. This whole thing was proposed in a matter of weeks and funded in a matter of weeks and operational in a matter of months. That part doesn't happen. Okay. So beginning in 1959, this became one of the earliest funded projects of DARPA, which itself was founded right after the launch of Sputnik. This was like bang, Cold War priorities. This became known as the Navy Transit System. They were indeed, once the US succeeded in finally launching some satellites, after some frustrating delays, A subset of these were built by and for the Navy with transmitters on them to beam down basically I'm here now kinds of instructions for use with naval navigation for things like ships at sea. I mean, it's a breakneck speed compared to maybe that there's a thing overhead. Maybe we could do this crazy thing. Let's get it funded and build it into the Navy. Very, very
Were they using timing?
They were not fancy clocks yet, but they were using clocks on board to beam down I'm here now. Information.
By the way, the GPS pressure in the early 70s was because soldiers were getting lost in Vietnam.
Yeah, so the military origins didn't evaporate right away. Exactly. Yeah. Okay. So again, as certainly Peter knows very well, he's an amazing student work on this as well. In parallel with those developments, atomic frequency standards, or what are often simply called atomic clocks, were improving in many government research labs in the US and UK and other parts of the world. So that by the mid-1950s, it was typical to be able to achieve a stability of these clocks to parts per trillion, which is all out of proportion to what had come before. So that's like losing on the order of 100 nanoseconds per day, which again, to us today doesn't sound so great, but that was really quite extraordinary in the mid-1950s, roughly a decade after the end of the war. And again, there's some really classic work by our colleague Paul Foreman on a lot of these kind of microwave electronics transformations coming out of the wartime radar and proximity fuse and related projects. Peter did a lot of those as well. So it was actually a naval research laboratory researcher, Roger Easton, who wondered if they could combine these ideas. Let's put really accurate clocks, these new atomic frequency standards, on those purpose-built satellites for beaming down I'm here now or time-stamped information. Couldn't that be a great improvement for things like naval navigation? Unbeknownst to Easton at the time, which is how things always seem to go during the Cold War in the US, there was a parallel effort undertaken by the Air Force. And of course, they were the main rivals of each other. Each was highly classified. So the Air Force was working on something called Project 621B. I don't know if there's a 621A. I don't know where the name came from. That was actually kind of highly classified. And their idea was to put these atomic frequency standards on satellites, not for navigation, but for targeting. I want this bomb to go there as much as I want to know where my ship is. Another high priority in that case for the Air Force. So these were both happening starting in the late 50s and really picking up speed through the mid-1960s. A decade into that, the Defense Department said we better consolidate. So starting in 1973, just over 50 years ago, the Pentagon formed the first joint program office for what they began calling GPS, based at the Los Angeles Air Force Base. You can see another staged photograph. The whole program was under the direction of the Air Force Colonel Brad Parkinson, shown in his dress whites, clearly cooperating now, Air Force cooperating with the Navy and with the private contractors from Southern California, in that case, a representative for the Aerospace Corporation. And so the main goal was, as the Air Force thread had been along, guidance control for weapons delivery, what would come to be called so-called smart bombs or smart weapons. The first purpose-built satellite for this new program was launched from Vandenberg Air Force Base not too long afterwards, in June 1977. And again, it had one of these very fancy onboard clocks, and it began doing test runs at the Army's Yuma Proving Grounds in Arizona. Here, I love this photograph. Here's Senator Barry Goldwater from Arizona visiting the Yuma Proving Grounds, clearly listening into the man pack. I don't know what he expected. But there he was. That was a place to be, to see these new tests in 1978. And this generated tons and tons of what we often call the gray literature, tons of, not all of it classified, but not peer-reviewed, published in the scientific journals, kind of operations reports on these early test runs. And so to keep the whole organization motivated, Colonel Parkinson used to put these posters up around the walls. I'm not recommending this for the PHI, right? But it was motivational posters. The missions program office is to drop 5 bombs in the same hole, build a cheap set that navigates, and don't you forget it. That's going to motivate young people. And indeed, they began getting that good at these at least kind of controlled proving grounds operations by 1978. 10 years later, this was then put into the US targeting system for nuclear-tipped cruise missiles. So it goes from sort of one operating satellite and test runs in Arizona to using this to rely upon for steering nuclear weapons. Pretty quick. Okay, let's come now to this last part, the dueling relatives. What is how do we bring the relativity back in? So as we know, the speed of light, at least in human terms, is fast. I mean, it's 1, right, for me, but for other people, it's fast. It's 300,000 kilometers per second. And that means light travels, roughly, 30 centimeters, about 1 foot in 1 billionth of a second. That's fast. So to achieve sort of operational spatial resolution on the order of 1 meter, you have to trust a network of these moving clocks to remain synchronized to basically to a few parts per billion. You have to have a disciplined sequence of clocks that are operating with an error budget of about 3 nanoseconds. So by the mid-1960s, more than 10 years into the ready availability of atomic frequency standards, not only in kind of pristine laboratory conditions, more and more researchers, including in totally unclassified basic research settings, began to realize that if you want to start using things like a network of moving satellites sending electromagnetic signals down to the surface of the Earth to navigate, let alone to drop weapons, then you really, really have to start worrying about relativistic corrections, right? Because the speed of light is not infinitely fast, as we know. And so there's early work done, for example, by a Japanese astronomer published in the Astronomical Journal in 1964, an article in PRL in 66 by a researcher at that private contract, the Aerospace Corporation that I mentioned, basically trying to say, given what was known in the outside the classification about things like projected GPS satellite orbits, how high would they be, how fast would they move, what are the types of relativistic corrections one should have to begin to think about in order to preserve or actually hit this aimed for operational accuracy of about 1 meter in spatial resolution. So as a reminder, there are these first 2 effects that had been identified decades and decades earlier, time dilation and gravitational redshift, and they both come into play, but it turns out with opposite signs. Nothing about GPS. So let's take the time dilation first. The satellite's moving fast, at least with respect to us on the ground. They move with several kilometers per second. That's not the speed of light, but it's quicker than the red line by a lot. And so you have to worry about things like time dilation to the required accuracy, right? To get spatial resolution of meters, temporal error budget of nanoseconds, then you really have to start worrying about that relative speed. So that's to say that we on the ground would watch the clocks on the satellites ticking more slowly than our reference clock next to us, right? We'd see them time dilate, of course, they'd see us time dilate. But the satellites are also high up, right? They're on the order of 20,000 kilometers above the Earth's surface. They're in a much weaker gravitational potential than we are. So they should be less subject to gravitational redshift, they, meaning the satellites, than we are. So the orbiting clock should be less slowed down by this other relativistic effect compared to our reference clocks. And so they don't exactly cancel. They have to calculate each carefully and and check out the residuals. And the strictly analytically predicted difference was basically a few parts per 10 billion between these 2 different relativistic effects. As I say, they don't quite exactly cancel. And again, this is the kind of error budget where if you ignore this, then you'd lose the required accuracy for GPS within minutes, right? And the errors would simply propagate over time. So some early on in the early 70s, when this first sort of joint program office first was organized, there were some DoD engineers who were skeptical about all this stuff. They were experts in satellites. They were experts in what was called time transfer, using electromagnetic signals to coordinate clocks far apart from each other. And they were skeptical that any of these very strange sounding relativistic corrections had any role to play in this new high priority technology. Others, it turns out, realized they had to worry about relativity, but double counted effects. They would basically count redshift and time dilation, or how it worked out. But they would get off by a factor of 2 because they took relativity in that sense sort of too seriously. So this is not to tease the engineers. I think it was non-trivial to apply very simple looking equations to an operational, complicated military technology with lots of moving parts. The skeptics of these ones who said, keep your relativity off my clocks, they were quieted down pretty quickly with that first launch in 1978, or 77, excuse me, of the first purpose-built GPS satellite. They carried on board a relativity switch. And Peter wrote about this at the very end of Einstein's clocks. It's fun to find this stuff. So the engineers on the ground, well, let me back up. So the engineers said, you physicists can't touch our nice clocks, I'm paraphrasing, right? You're not going to put your silly relativity stuff into our pristine engineered equipment. Their compromise was to put basically a patch of code that can be transmitted from the ground, send it through telemetry to the satellites, to throw a switch and change the software, right? To have a software switch that can be activated from the ground. When the signal was sent, it would activate a kind of, it would report out sort of the wrong time or a different time from what the onboard clock actually said. So reported time from the satellite would take into account these relativistic effects. The onboard clock would still tick unmolested, right? And so that's what they did to make sure that, as a way of testing, whether all these very strange sounding ideas about warping space-time had to be taken into account at all. And so this is the measured time difference between the reference clock, the time difference between the reference clock on the ground and the orbiting clock over time. And indeed, the difference in rate was a remarkable test of the relativistic prediction. It was a test within about 0.5%, which back then was really very good high precision test of GR. And so first of all, the predicted offset in rates was real. It matched to remarkable accuracy the sort of parts per 10 billion that had been predicted ahead of time. And that began quieting the engineers. The effect is real. Then they said, okay, send up your patch, your software upgrade. And indeed, then the rates became essentially parallel. So once the onboard clock was told to start lying about its onboard time, to report out a relativity adjusted time, then indeed the measured time on the ground and in the sky became essentially the same. Yeah.
Well, why was the gravitational redshift controversial? Hadn't the Pound-Repka experiment already been done and conclusively showed that?
Yeah, to every single reader of PRL. No, to a small fraction of readers of PRL. You should remember, Shep, that unlike this glorious citadel we're in today, relativity itself, general relativity itself, was really on the outskirts for a long time, even among the American physics community. Now you have to get these, a bunch of highly professional engineers who would come up, let's just say, on a parallel track. So citing something that happened at Harvard, in a Harvard Tower of all places, this was not in itself compelling. And so you really have to show it on their terms, and that's what I say.
Is there a culture class?
It was at least in part a culture class, and it really wasn't just physics versus engineering. It was subfield of physics. The relativity community was really quite insulated at that time, compared to all the other groups that they had to coordinate with and work together. Much of this part now being done behind a secrecy wall. Not so straightforward. I'll come back to some more examples of that actually. So you and I been transported back, and we were stamped our feet. You must, but we used to wonder one until the engineer said, "Oh, okay, right." Your little software patch seemed to do the trick. This result was published in the open literature, but not in a peer-reviewed scientific or engineering journal. It was published in one of many kind of frequent workshops organized by the Army Electronics Research and Development Command. They held a workshop at a base in New Jersey, it turns out. This wasn't classified, but also wasn't super easy to find, the results of this actual test, right? After the successful test, which was conducted in 1978 with that first satellite, after that, they did what was called a factory offset. So pre-launch, they would have the onboard computers pre-compute the relativist corrections and report out for all the time the relativity adjusted readout time. So they'd have to sort of tell the satellites to change your tune. Even that sometimes didn't work. I found some of these in the archives. Sometimes the chips were actually misprogrammed. The various agencies had to sort of embarrassedly say, "Please send us your chips back. We'll send you new ones for free. We're sorry about the mix-up." So just during the factory offset, took a few iterations to get straight as well. Nonetheless, they did finally agree that the relativity had to be taken into account. But what about that third sort of relativistic effect, the effect of rotation, the so-called Sagnac effect? In no lesser authority than Landau and Lifshitz, which when translated into English in the mid-1950s, remained the dominant authoritative textbook on GR, even in English, for a long time. Remember, MTW, Weinberg's books, those came out in the early 1970s. Wald's book was 10 years downstream from that. The book to go to, where many experts in the field in the United States had learned relativity, was the first English translation of the classical theory of fluids. In no lesser an authority than that, they have a whole section on rotation, and they actually say, as you can see, clocks on the rotating body cannot be uniquely synchronized at all points. The Sagnac effect is real. It's a prediction of relativity. Live with it. That's even separate, as I say, from kind of frame dragging or lens tearing. So beginning in exactly the time that the first perpendicular satellite was launched, behind the fence in this high priority military set of tests, a quartet of physicists outside the fence who were, as I'll say in a moment, highly trained experts in relativity and astrophysics, were not associated with the GPS project at all, began getting concerned based on this third relativistic effect, the Sagnac effect, that GPS could never work as advertised. They didn't have classification clearance, at least for this project. They weren't working on the guts of the project right away from the experts. They were saying what's come out in the press about the ambition to have a network of satellites giving 1 meter accuracy specialism, that simply cannot work from first principles because rotation will always mess things up. And so they start publishing in peer-reviewed, sometimes quite illustrious journals like PRL, like one of the earliest issues of classical quantum gravity, in an electrical engineering journal related to, again, things like time transfer. They begin publishing a series of critiques of GPS in principle because of this third relativistic effect, because of relative
So
rotation.
they're saying it can't be coordinated, but you couldn't even offset that effect to understand where you were.
You've read ahead, Peter. So that, at the time, that was ambiguous. I won't give away the answer just yet. Okay, what you said was right. So the point was that they have limited access to the classified stuff. They're getting things through, refereeing from experts in relativity and beyond in places like PRL, saying this unavoidable, unsynchronizability due to rotations will lead to offsets thousands of times greater, or what they considered relative errors, thousands of times greater than the operational requirement of microsecond synchronized clocks. So instead of having 1 meter accuracy, these things they argued would never be more accurate than 3 kilometers, which is not very good for dropping 5 bombs in 1 point. So they start publishing this starting in 1977, and they continue again for about 10 years. Yeah, yes.
Sorry, just check the timeline here. Is this before or after there are dropping bombs in holes?
This is coincident with,
Okay.
it's like starting before, but when they start dropping 5 bombs in holes, that was not front page, that was still largely classified at the time. So the fact that the relativity switch had worked, that was published in a non-classified but kind of gray literature out of the way thing. The outcomes of these tests was being documented like crazy, but mostly in classified forms. Good. So this is published, for example, the end of 1977, one of these first critiques. The satellite had been launched 5 months earlier, and the test hadn't been done yet. The last of these that I'm showing here is from 1985. So it's really coextensive with that same timeline. Good question. Okay. So who are those folks? I won't go through all this in detail. They were, by and large, very well-trained experts in things like relativity and astrophysics. So Jeffrey Cohen was a professor on the faculty at that point at Penn, PhD from Yale, postdoc at the IES. His dissertation was on rotating masses and their effect on numerical frames. That's all this person thought about, right? Since graduate school. And likewise, Harry Moses was more senior at UMass Lowell, fellow of the APS and New York Academy of Sciences. Arnold Rosenblum was an expert in things like supergravity, very early, expert in efforts to try to quantize gravity, thinking very abstract kind of mathematical physics and relativity. Had even won an award from the Harvard Smithsonian. And likewise, Angelos Galafouris had an astrophysics PhD from Brandeis as well. And he was often a visiting professor at Penn, so he knew these folks personally, and was also a research staff scientist at the Naval Research Lab, but not on the GPS kind of part of it. They were siphoned. That's the kind of outsider quartet. We start getting worried about rotations will ruin GPS from the start. Okay, so the framework for incorporating all these different relativistic corrections within GPS had been worked out by 2 scientists based in Boulder, Colorado. One of them at what was then called the National Bureau of Standards, what we now call NIST, National Institutes for Science and Technology, Standards Technology, and then another on the faculty at UC Boulder. That was Neil Ashby and David Allen. And they began working out a series of basically coordinate systems, right, within which to do all the other hard stuff for GPS. And as you can see, none of these is showing up in PhysRev D or PhysRev letters, right? This was actually, again, an unclassified government report released by the Commerce Department because Commerce included things like the Bureau of Standards. So that's why it came out as a Commerce document, not the NSF or the DoD. They published one peer-reviewed article in one of these engineering journals devoted to aspects of electrical engineering. And then if you knew to look for it, there was an unpublished tutorial written for one of the Air Force contracts. Of course, it was not released broadly at all. And so these things were written down, but not super easily accessible and not in the same kind of, not showing up in the same reading feed, so to speak, for other physicists who might care about things like relativity and motion of clocks. So an outsider quartet, right? Cohen, Moses, Rosenblum, and Galafouris. What they did is they solicited their own post-publication reviews. This is a nightmare. This is published in a peer-reviewed journal by Ashby and Allen. So it's come out in an engineering journal. We don't trust it. They sent it for their own refereeing by people they considered sort of not interested, experts in relativity who had nothing to do with this work. So a post-publication peer review. They sent it to a scholar in what was then West Germany, Dr. Seifert, and then a colleague in Britain in mathematical relativity. Seifert wrote back a 5-page referee report in English that only gets more nasty, right? I'll show you the first page. It didn't get nicer, right? And then with typical, tight-lippedness, the British guy wrote only 1 page. So anyway, they both are scathing about this already published report article that was laying out the coordinate system for GPS as being used by this high-priority military project. So here's what Seifert says. Unfortunately, this paper, when it was being sent out for post-review, seems to present neither correct nor a clear description of the problem. It uses pre-relativistic language. You can imagine how rude that is. Pre-relativistic language, Newtonian 3 vectors. It's disgusting, right? In fact, the fundamental equation 1, on which the rest of the paper is based, obviously does not take some important effects into consideration, including the effects of rotation. This is what will actually dominate the results as they stand, cannot be used. That's review number 1 from Dr. Seifert.
But I see he's talking about the lens steering effect.
Among other things, he's even worried about kinematic rotation. The equation 1 says there is, or that even that's going to swamp because of this good factor of 3,000, right? Meanwhile, from Britain, Dr. Clark writes in saying this paper is quite unacceptable as a basis for a theory of measurement within GR, because the underlying assumptions are incompatible with relativity theory. Again, mostly they ignore the dynamical effects of the Earth's rotation. The metric they use is a static metric transformed into rotating coordinates, but does not include all the relevant effects. I recommend that no reliance be placed on these authors' results unless they can be obtained by other means. So now that's when the outsider quartet has gotten back in the mail. They then do what they felt was their duty, and they send these to the Air Force, along with an unsolicited grant proposal saying, give us money, we'll help you figure it out. Because again, they're not dumb, right? They have PhDs in physics.
The Cypress writing from a military academy.
Yeah, and they're trying, exactly. You can see these folks are smart, saying, who should be listened to? Who will the Air Force listen to? That's right. So now some of these members of the, again, sort of outsider quartet forward those really quite remarkable referee reports, along with their own proposal, saying, we'll help you understand this. Although described as a navigational system, GPS constellation satellites will greatly benefit the Defense Department. Let's not fool each other, right? This is a military project, they're saying. And for that, to be able to target cruise, ballistic, and precision missiles, you need high accuracy within 1 meter. You'll be way off because of what's already been published in the peer-reviewed open literature by their articles. You'll be off by a factor of around 3,000. Meanwhile, they go on to say in their grant proposal, the mechanism by which relativistic corrections are actually carried out in the real GPS system, still very early in the stages, does not seem to be available to inquiries, let alone published in either the open or classified literature, according to telephone conversations with various contractors. They had to call it, how are you doing relativity? IBM, Magnavox, Aerospace. And what they report is all the people who got on the phone said, oh, it's fine. We're just using the Ashby Allen, the Boulder, Colorado system. And that's exactly what had just been ripped to shreds by Seifert and Clark. And unfortunately, that's erroneous, as we've now convinced ourselves because of their own calculations and the expert outside review. So the cover letter that accompanied this grant proposal, Skelly first goes on and says, remember, I'm actually a licensed engineer. I understand the practical approach. I'm not trying to worry only about very esoteric things. We're worrying about getting a legitimate and neutral opinion. They're worried about special interests. Right now, only the contractors are saying the contractors are doing it correctly, is essentially what he's arguing about. You can understand we're severely handicapped by the unwarranted secrecy. Therefore, all we can do is speculate on how someone with intelligence, yet without training in relativity, who's willing to grant that was possible, there might be a smart person who didn't take GR. How would they do it? How would they solve the problem at hand? Since they're not giving us all the details, and it looks like what they're doing is going to be terribly wrong. Then the next letter to the same Air Force general from the same outside committee says, the stakes are really important. If you get this wrong, then we will trigger nuclear war. I promise you from the nuclear war. So why do we have to worry about this? And this is work, again, completely correct for the time. A classic work by one of our colleagues, John Mackenzie, has gone through examples like this in great detail. The biggest worry is that if you don't have sufficient accuracy for targeting, then you can trigger a runaway arms race. Because if you can't drop the bomb where you want, you have to make a bigger, the argument was you need a bigger payload to take out everything within a larger radius. And so accuracy implies you can get away with a smaller set of warheads, but if you can't ever deliver that accuracy, you're going to trigger, again, a runaway arms race. Moreover, the Soviets are very smart, and they'll call our bluff during negotiations, in this case, by this point, we're up to 1984. In the midst of all these sort of next generation very hard to negotiate agreements with the Soviets. So they'll know we're bluffing. After all, land ownership should come from there. Meanwhile, NATO relies on us. So the whole thing depends on accuracy and timing, and you can't possibly do that. So enough of those letters will actually get the Air Force to respond. And so a brigadier general says, we need our own separate blue ribbon committee. So we put together what was called an Air Force Study Board Commission that was chaired by Clifford Will. There's a younger Cliff, one of the briefings he had to give at the Pentagon. So this is, it was a committee, as you can see here, with several leading experts for academia in relativity, including early generations of experimental tests. I think Pound was in this one, or people who certainly would have known about Pound Repka. Robert Vesso was here, was nearby. Some experts from government labs, from industrial markets, okay? And their idea, their charge was to take all these criticisms seriously and report back to the Air Force. Cliff, by the way, had recently finished his own PhD from Kip Thorne's group at Caltech. His magnificent monograph was right, kind of fresh hot off the presses, still in print to this day. Cliff was in some sense a really inspired choice to lead this group. Except as it turns out for the following. So Cliff had told me this when I spoke about it, he and Nico wrote about it in their books, I'll let them use their own words. An awkward moment occurred midway through the year-long study, when the Air Force Study Board staff person asked me when I'd become a naturalized US citizen. I replied I never did. He was still, at that point, a Canadian citizen here on a green card, a fact that was evidently overlooked on the CV he'd already submitted, right? Someone had to check. There's a problem because all the Air Force Study Board studies are initially classified. And so after some urgent phone calls, the staffer managed to get a general to retroactively declassify Clifford Will's own study, so Clifford Will could be working on it. Right? That's what it was like. That's how we found the Canadians back in the day.
So this is 84, 85?
Yeah, exactly. That's right. And it turns out in parallel with the Air Force Study Board, there was also a Jason study, which shared one member in common that can coordinate, Douglas Erdley. And the Jason's group included Freeman Dyson, Paul Horowitz, Bill Press, Mel Ruderman, Sam Treeman. This was taken very, very seriously, right? So Jason's took a year to write their report. The Air Force group took an extra year. They had a more extent, wider charge, but they basically came to the same conclusions. So let me wrap up. Here's what they both concluded after this very detailed study. Both panels conclude that the original work on this coordinate system by the Boulder group, by Ashby and Allen, had been correct to within requisite accuracy all along. They don't need lens Turing. They can nonetheless maintain a few nanoseconds error budget in the synchronizing clocks, even for observers on a rotating thing. And it really came down to basically gauge artifacts. It's what we do all the time. It's just these were gauge artifacts that many of which are being debated, in classified documents. So in this original article that had been published in the Engineering Journal by the Boulder Group, the Air Force Study Group, led by Cliff Will, says we've independently derived their first equation, and it's correct. It's actually just fine as written. It's true it's written in not the language of relativity, and that's not surprising, they say, because most relativity textbooks are most tangentially concerned with real-world measurements and systems. But back in 1984, that was nonetheless a true statement. They go on to say that this outsider quartet has basically independently rediscovered the Sagnac effect. It's real, and it's not going to do them. It's actually for exactly what Peter had said before, that this is a calculable offset, not a differential rate. Right? So if you're constantly talking to the satellites from the ground, you can basically send updates and then track them and then update them again. It's essentially a calibration and not an uncharacterized error. Okay. And so, and this exact identical wording is in both the Jason report and the Air Force report on this point. The Sagnac effect is not uncontrollable errors, are completely computable corrections because the orbits are otherwise known so well. So Cliff shared with me his handwritten, this is what used to be PowerPoint, his handwritten overhead transparencies. He had to brief Air Force generals on relativity and say it's going to be okay after all. So he gave himself a few slides. There are things that affect the rates of clocks, like time dilation, gravitational redshift. There's a separate thing, this offset. Where's your zero of where you're starting to measure time from? And that will indeed be a legitimate disagreement, but one you can overcome by just overwriting it with updates from the ground. And moreover, groups have actually been able to successfully demonstrate this Sagnac effect correction with both commercial aircraft and just long distance on the ground kind of telemetry. So they knew how, the experts in time transfer, as it was called, knew about this and had international treaties over how to handle this already. This will not doom GPS. So how does it actually work? I found this really fascinating. What Ashby and Allen had set up, and what is, to my understanding, still what's done to this day, is to construct an Earth-centered, non-rotating reference frame. So put the origin at the center of the Earth, but it watches the Earth rotate within it. The coordinate time in that matches no actual proper time. No one's moving up according to that. But within that reference frame, you can map out every single observer and every single moving clock. But from all your primary calculations in this convenient fictitious reference frame, where you're anchored now to a clock that's arbitrarily far away from the North Pole, so it's not affected by any of these local gravitational effects. You do all the calculations in that convenient fictitious reference frame and transform back as needed. And then you have residual corrections for things like calibrations. So you actually take advantage of the fact that coordinates can't matter, and we can use what's convenient. Okay, let me wrap up. So by the late 1970s, both insiders and outsiders agreed this will only work with relativity. The era of saying leave relativity out of it had gone. They still had almost 10 years worth of disagreements over who's getting relativity correct. And there were distinct, conceptually distinct things they realized they had to worry about. And the question remained, were these things being incorporated correctly? And that was really hard to agree upon, in part because of classification, in part because of trade secrecy, in part because it really was different subcommunities with different languages, different notations and favorite references, all under the shroud of high priority, large classified military. How did it come into use for the rest of us? Unfortunately, through tragedy. Some of you might remember, in 1983, long before there was a single operational GPS system in the United States, a civilian airliner, Korean flight 007, was shot down over Soviet airspace. It was a flight from JFK in New York, JFK Airport, to Anchorage, Alaska, and the final leg was to Anchorage to Seoul. And it drifted quite far off the intended path and was shot down by Soviet military jets, with many hundred people killed on board. Roughly 2 weeks later, US President Reagan announced that when GPS was operational, a few more years in the future, there'll be a version made available for civilian use to avoid these kinds of tragedies. And indeed there was, but it was subject to a kind of what was called selective availability, which means the government selects not to make it available to us, right? So there was an intentional degradation by a factor of 100. There was a highly encrypted military grade signal for which you could indeed achieve 1 meter accuracy. And then a purposely degraded signal beamed down an open channel for the rest of us with roughly 100 meter accuracy. And that's what starting when GPS was made available until 1988 for the civilian market. That would still, it was arguably enough to avoid this kind of tragedy. It won't get me out of my kitchen. So in the closing days of the Bill Clinton administration, enough studies have been done to say the commercial benefits of opening this up to greater accuracy are large. The national security risks are actually quite low. So they ended selective availability again with just a software upgrade. They didn't have to change any hardware. They just beamed it up saying, stop degrading the second signal. And here's the error bars overnight. So with the development of inexpensive receivers and ubiquitous mobile devices, Einstein's beautiful general theory of relativity now helps billions of people all over the world find their place in the world every single day.
Great. We have just about 5 minutes for questions, so I'll alternate between Zoom questions and in-person questions. Folks on Zoom, if you can raise your hand, I'll call on you and we'll be able to hear you. I saw Ansi.
Yeah.
Just quickly, I'm curious about, so this is a really interesting history of how the Americans had it used. What were the Russians
Good.
doing at the same time? Like they're seeing the Americans putting these satellites up, these signals, like what's their response and how are they?
Honestly, thank you so much for raising it. So the short answer is I don't know. And so we have a very dear colleague behind many of us named Asif Siddiqui, who's a world expert on the history of Soviet space technology, including aerospace. So he's been very helpful. He's been able to find, when I asked, much later review articles from the post-Soviet system, where they list all 3 effects and here's how they get dealt with. We have not, he certainly has not, and I have no Russian language skills, been able to find anything from before it was clarified here. Was it clarified there earlier? Do they have different questions? I don't know. The short answer is the Soviets did build a parallel, and I think comparably accurate system. It was called GLONASS. I was thinking it as Glasnost. It's GLONASS, but I think it's still in operation. So clearly some of them must have faced similar questions, and I wish I knew more. That's the short answer. Thank you.
They probably respect their physicists more. That's my guess.
I won't speculate, but I'd love to know more than this.
Dennis.
Thank you. Thanks, David. That was great talk. I have a question about the use of coordinate systems there, right? So in sort of mathematical GR, theoretical GR, different coordinate systems and distinguishing between coordinate effects and coordinate independent structures, but also, very much more skilled use of different coordinate systems to describe the same target system really took off in the 1960s, right? And so I wondered, did the developments in the 1970s on GPS, did they draw on that in any explicit way, or did they draw more on older stuff? Like you said, they referred to Landau-Lifshitz. So was it decoupled, or was there an influence?
Thank you, Ben. I think they were, as far as I can tell, they were totally decoupled. So
Right.
one, I might be missing parts, of course, it's lots are still classified I haven't been able to find. But what I found was even when Clifford Will was sitting down in his own notes to get ready for briefings with his group, he was really starting in, and I think appropriately, in an explicit coordinate chart. And he was then mapping through why would the rotation be, amenable to calibration updates and so on. So even Cliff, who was trained by Kip Thorne, who, in the early days of MTW, was writing down saying, we don't need annual coordinates, we need coordinates that are useful to users on Earth. I think that's why it would have started that way. And so the traces I've seen, even in the unpublished, literally handwritten notes to prep, we're not doing fancy Bob Wald style, highly geometrized, coordinate independent things. I've always seen people starting from a lineup, limited to writing down ds squared equals, and then trying to calculate sort of, proper time intervals and all the rest in a way that frankly, I would still do it because I'm very bad with those fancy geometrical techniques. So I haven't seen any evidence of that kind of interpolation. The physicists who, in addition to Clifford Will, who were on the Air Force Committee, I think we're also, if we go through the names, we'd expect them to do things as I've described.
Hmm.
People like Douglas Erdley, and who else? Richard Matzner, of course, more fancy. I didn't see them even certainly not in their published reports, and even in the few sets of notes I've seen, informal handwritten notes, doing anything like what you're describing, though indeed it was available on the Earth, right? There were people who were cultivating those techniques. It wasn't, I think, what this particular group was most familiar with and most comfortable. That's at least my current best guess.
Great. Thank you.
Actually, my question is not on the relativity, which is fascinating. Speed of light does change in the Earth's atmosphere.
Yes.
And I would imagine, weather and latitude and all sorts of stuff should matter.
Yes.
Is that all put in, and do they look at the latest weather reports?
So I don't know about the use of the latest weather. I imagine they do, but you're certainly right. There's a ton of work on fancy ionospheric physics and the propagation of real waves in the real medium, as opposed to just writing C equals 1. So that was not controversial to the engineers.
Right.
In fact, many of them had decades of experience with that. They've been launching, sounding rock. So that's what a lot of these folks were already. That was their kind of bread and butter. Let's say I'll call it roughly being atmospheric or let's say transmission effects. It's a real medium. There's noise. But then we're confident they could control that noise budget to within 3 nanoseconds.
Right.
And so these other things looks newer to them.
Good.
Yeah.
I'll do a quick question and then go to Shep. Jonas asks, is it correct that the Clinton administration descrambled the civilian signal because the European Galileo system was developed and would anyway give a civilian position as good as the US military?
It's a great question. I don't know the exact timing. There certainly were close in time, and whether one was the sole cause of it, I don't know. I've spoken with other folks who seem to have been involved with the US decision making, and a lot of them I think were doing, as far as I'm saying, independent calculations about national security implications versus commercial market, even just within the US. So the certainly correct question that the Galileo system was under development and was seen as a complementary, if not rival system. I don't know if that alone was enough to convince in spring of 2000 for that switch. I'd love to learn more about it.
Yeah, first a comment about Ramesh's point. To get centimeter accuracy, geodetic receivers use dual frequency, exactly for the ionosphere, to take that out. I have one question, which is, you would ask, why do you need VLBI anymore? Not from the perspective of looking at black holes, but from the perspective of using VLBI and the celestial reference frame to look at the motion of tectonic plates, for example.
Yeah.
And my recollection and understanding is that there are a few things, at least one, that GPS can't calculate, which is change of the length of day. Because the Earth is spinning, but it interacts with the atmosphere.
Right.
And you can get millisecond changes in the length of the day.
Millisecond?
I thought it's
But over integrated over what, over a year, or over a decade?
I think over weeks, because I believe that to find nuclear subs.
Yeah.
They have to do VLBI roughly once a week to solve for the change in the length of day.
Great. So I don't know anything about that, but I'd love to learn more. We have a friend we can ask when it comes to tracking, history of tracking subs. I'll go ask Naomi Ruskies first. But I don't know, but I'd love to learn more. I have, let me just just quickly, I've seen nothing of that come up in any of the traces behind the scenes or in the reports from either the Jasons or the Air Force group. And I might be forgetting it. I'll go back and double check, but I don't recall that in this. There was this expert community on what they called time transfer, which again was mostly kind of geodesists and engineers of many kinds, going back to the traditions that Peter wrote about, back in the days of Poincaré. So some of them would have certainly known about those things, but I don't recall that in these particular discussions. I'll go back and look again. Yeah, certainly.
I think one thing that prompted the non-degradation of the signal was that you could do differential GPS. You take a GPS receiver, put it on the lighthouse,
Mhm.
you know, the lighthouse isn't moving, and then you see where the GPS is saying it is, and then you just offset by that, you put relative to the lighthouse. That was an easy fix, and it got around the degradation problem.
Right.
But, and the other thing I was thinking of is, I'm amazed at how late these discussions are.
Yeah.
I mean, by the early 80s, certainly by 83, Francis Everett and the people doing the Gravity Probe B
Right.
had 20 years of experience trying to propose frame dragging to NASA.
Right.
And it got canceled because it was too expensive,
Yeah.
and they wanted to do it on the shuttle. They ended up doing it on a Delta rocket.
Right.
But I think that, those discussions with Schiff and Everett and lots of relativists
Yes.
were pretty clear about how to calculate something like frame dragging. So I would have thought that the Signac effect would have been pretty child's play for that period.
Again, I think things look so crystal clear to us, in minutes, right? So I think wasn't William Hamilton from that group as well? He was on this Air Force study board, for example.
Mhm.
I thought he was in his earlier days had come from the Stanford group. I think that's right.
Mhm.
So it's not that these things were unknowable. The question is, did the NASA knowledge percolate through to Air Force? Not always. We know that was not an easy boundary. What was it in practical terms for these, groups of the sort that Peter you've been describing for a long, long time that were, neither physics nor engineering nor military nor civilian. They were this kind of melange, a training zone. And not all the information was flowing, equally. And you think about someone like Richard Madsen. This would have been homework assignments for his undergraduates, part of it. And yet this group worked for 2 years, right, to really clarify. So I don't want to say it was trivial. It was knowable, but not known.
Good, thank you, Dave.
Thanks, Peter.
Okay, great, thank you.
Great. You have kicked off the new season in a spectacular fashion.
Let me just do a quick note. Next week, we'll be partnering with the CMSA, so we'll be doing it downstairs in the basement. So just keep an eye out for the location of next week's foundation seminar. Thanks, everyone.